Okay, any questions on the homework? Let's start there. I know several of you have turned in homework 6. It's not a terribly difficult homework set.
I haven't started.
We don't put it off too long.
Well, I actually, I did start the quiz on it.
Started the quiz
I
with it?
did like 5.
Okay.
I think my number one problem with the homework is I'm overcomplicating it.
Usually. That's usually the problem.
I started with the quiz, I looked at the quiz, and I was like, this one was that bad. I got there a few of them, and I was like, I really need to look at chapter 5.
Does anyone need help with the quiz? Any questions on it? Would you like to address that as well? Already had one person come to me today and ask about the quiz question. I'd like to talk about that as well. I see the quiz and the homework is your place to learn.
The quiz is due today and the homework due Monday.
I've lost track.
Okay.
Technically, the quiz is due Monday, and the homework was due Wednesday.
They don't count off though for later on.
I don't count it off for that.
Okay.
But we do need to catch up at some point.
I will do it before Wednesday.
Yeah, I need to start catching up on quizzes. Mondays, like 8 o'clock, like I come home, like, there's a quiz, and then I fall asleep, and it's just like,
Well, the chapter 7 stuff looks like it gives you 2 weeks for it.
Well, the student that came and talked to me was talking about exams, and I think on the syllabus I've got 4 exams listed, but we talked about that before. We said we have 3 exams total, and we'd have the project count for 40% of your grade. Is that correct? Is that what we decided? I think that's what we had decided. In any case, the way I'm going to count it, let's see, this is tonight will be our 5th mini test, right? So this will be the first question of what will be the second exam. There'll be 3 more of those, and then the only other thing we'll have is the final exam as far as exams go. The final exam, I don't know how to spread it out. I don't really want to give you the final exam during regular semester time. First of all, we're not supposed to. In the second place, I would rather give that to you and push that off until finals week. So we'll have an actual final exam. If you guys, I was going to say you could come in 4 days and take 1 question each day, but I'd rather not do that. Let's just bite the bullet and get it done, okay? But during that time, during the last bit of the semester, you're going to be working quite a bit on the project. I want you to have time to focus on that. Not have to worry about many exams.
I'm buying a book since this class started.
Since you walked in the room and saw us, me teaching.
No. It started chapter 6.
It's material.
That Monday, chapter 6 was Monday, whatever that was. I don't even remember. It's like it's black hole. It was just like.
Well, let's see. I worked a lot of problems for you from chapter 6. Hopefully they help you some. And I'll help you a little bit with homework questions on chapter 6. So really what we need to do is move on into chapter 7. Now chapter 7, I'm trying to get my slides loaded up. Chapter 7 has to do with the mathematical statement of the second law. Now, I'll warn you that this chapter 7, is pretty theoretical, but it's very useful. So a lot of the stuff along the way, you'll see a bunch of equations derived. I'll try to point out what's important. The derivation is not all that important. You don't have to derive everything in this class. You do have to know how to use stuff, and you have to believe in it enough, and you have to understand what all the pieces are that go into the equations so that you can use it. Okay? You also have to know when equations are applicable and when they're not. A lot of you try to use the ideal gas law, and that doesn't work very well. Okay? So just remember, equations don't always work in every situation. So the equations that I'm going to give you, or that essentially your author gives you, only apply to particular instances. You have to know when they are and how those things work.
Okay, so I was doing the dishes this morning,
Yeah.
and my daughter came over, and she had finished her bowl of fruity pebbles, and she poured it into the sink. And she said, "Oh no, I'm sorry." And I said, "Why?" And she said, "Because my grandpa yells at me whenever I pour fruity pebbles into the sink because I clog up the drain." And apparently this school has changed me because my explanation to her made her head hurt. I said, the viscosity of the the truth levels will not change, it's not a function of temperature or the plastic. It was just this insane explanation, and she looked at me, and her friend was sitting there, and she was like, your dad sounds smart. And Lexi knows enough about me, she did correct her, but, it was,
Oh, he's not really.
yeah,
I love it when your kid says, oh, my parents not smart.
I don't remember, it's just one of those things, it just came out all these words.
It's pretty good. Well, at least you've got a slightly different vocabulary so far.
Yeah,
Right?
I can sound smart sometimes to strangers.
So that's what a BS is for, right? Calculus science is for a BS. Now you know.
That's one with it. We got to talk about energy balances and everything this morning. Then she asked me, she said, because we were talking, she said, so I poop energy? And I said, well,
In a way.
yes.
Yeah.
And then I explained that to her.
In fact, you could tell her that there's more thermal energy coming out in the urine than in the drink, especially if the drink was cold.
I told her something like that. I
Yeah,
told
you
her.
laugh. Okay, you guys laugh, but honestly, all this stuff is engineering related. When I was in chemical engineering, the first project they gave us as seniors to get us interested in it was sizing a lauter ton. Now, a lauter ton is something that's used in making beer. That was trying to get us interested and get us to realize that chemical engineering is more than just boring stuff. There's some pretty interesting things that go on. They had some people come in from a few companies, I can't remember which company, but one of the companies made diapers. That's what they did. And as a chemical engineer, or an engineer, you have to solve problems. And they had to talk about the mass of waste in the diaper, the quantity of liquid, and how much likely it was for it to leak out. All these things, after they got used to talking about it and overcame the embarrassment and the initial, what is this? This is actually crap. After you overcome that part, it's just another engineering problem to deal with. So it was just interesting to me to see that somebody somewhere has to deal with all this stuff. Why didn't my presentation move up?
It's just not useful energy.
We got into that a little too, yes.
One phrase that I'm constantly telling myself is, when I look at something, is some poor engineer had to figure that out.
That is true.
Some more engineering.
Some poor engineers lost their job over that.
And
I bet General Motors did it, I don't know, that's improvement.
The brake.
With the Volkswagen.
Oh, the little
key.
Well, honestly, the Volkswagen thing, do you think any Volkswagen manufacturer cares? I think they're gonna take their car to the dealership and say, hey, fix this so that it reduces the loss.
But they still pay the,
No, but they're still jumping onto that lawsuit.
They're gonna jump on the lawsuit and say, can I get some money out of it?
yeah,
Right.
they're not gonna go against your business. That should be a simple issue. Lexi, she said, you know, saying that it's a smart car, it pulls the regulations.
That's a pretty smart car.
And then she said, well then,
I understand the issue.
what happens with
I
heat?
get it.
See, everybody's just jealous, like, I had to pay the program
Calories in the
car so that it's full.
And the waste.
So we do the same thing, it just makes it think that it's O2 sensors. So I think
Even if your body's not under sufficient.
Okay, I apologize that the slides are taking so long to load. Did you notice that in chapter 6, the statement of the second law we had was not really nailed down, it was more of a concept? And that's really what made chapter 6 so easy, is that once you understand that concept, it's really not that difficult. In fact, probably the most important result from chapter 6 is the fact that for reversible systems, the ratio of the heat flow is equal to the ratio of the absolute temperature. So that's probably the most important result from chapter 6. And then we use that to play around with various things. But in chapter 7, we actually have to integrate. Now I can go ahead and start talking about, let's see, I don't have the device in here anymore, but I can go ahead and talk about what a cyclic integral is. I mean, I hate it. You take all these classes on math, and you sit down in an engineering class, and the professor whips out some other math you've never seen, right? It's like, what is that symbol? I have no idea. So if I draw a symbol like this, you might look at it and say that's an integral sign with a circle on it. What the heck does that mean? Well, I can explain it really simply while our presentations are loading up. If you have a piston cylinder device, and you're considering the gases above the piston to be the system, you could push the piston up, reduce the volume in the system. You can pull the piston down, increase the volume of the system. Right? You can do either one of those. Now, if you were to, let's say, reference this particular height, so this, let's call this state 1, and you were to take this piston and move it up and then move it down past 1, then back up to 1, how much would the volume in the system change? No, right? Now, if you add up all the small volume changes, right, you move the piston to here so that there's been a differential change in volume. If you add up all those differential changes in volume, you get the same result. So this is 0. In other words, if you integrate on a cycle where the system comes back where it started for a property, you will get 0. Now, it turns out, this is very important, and we'll arrive at this in just a minute. But the idea here is that we could actually integrate, instead of integrating between two limits, we could integrate along an entire cycle. Does that make sense? Okay. Now, some integrals will give you a different result depending on the path. I mean, think about it. I've told you guys several times, if I take a box and move it from position A to position B, then it depends on the particular path I take as to how much work I do, right? So think with me. Let's call this state 1. And imagine with me that we take the box and we move the box to position B. Then we choose some crazy path and we move back to position A. If you integrated all those small amounts of work, which would be frictional force times distance along that path, you would get a certain amount of work, right? But notice it depends on what path I take. If I take a very simple path, I will get a total less work. I will do less work in that cyclic interval. Does that make sense? So it turns out that when you integrate some things like work, now don't be thrown off by these two symbols. This is just a small amount. This is also a small amount. We use this one when it's a path-dependent thing, like work. We use this D when it's not, when it's an exact thing. Okay? So the value of this integral, the amount of work I have to do, in other words, to move the eraser on the board from position A back to position A, depends on the path I take. So I can't say that this is 0. It will not be 0. It will be more than 0. Right? Does that make any sense? So that's an important concept we're going to use here.
So you're basically, you're adding up the boundary on the one and not the area inside.
I don't understand. What do you mean?
But like, on the one, you're adding up the area inside on the cylinder.
On the cylinder, yeah, you're tracking changes in volume.
But in that sense, but is that 0 because you're just making a linear motion up and down? So
It's 0 because the differential volume change here is negative, 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 right? We add a bunch of negative things. And then we add a bunch of positive changes in volume, and then some more negative changes in volume to end up back where we started. And you know as well as I do, since volume is a property of the system, it's just going to be what it was before. And so adding up all those small volume changes will give you a 0 at the end. Because you come back to where you
So
started.
for the other one, though, you're more or less adding up the distance of the travel. So
In a way, you could think of it that way, but really what we're doing is when I move the eraser from one position to the next, there is a differential distance, let's call it a ds, multiplied by the frictional force, which is a differential amount of work that I've done. Make sense?
So you're adding up the work amount.
I'm just adding up all the small amounts of work as I go along the path. The longer the path, the longer the distance, the longer the work, the bigger the work.
If you did the integral of work though with this piston, it would not be zero.
Right, that's the idea. It may not be 0. Now, it could be 0 if it's a reversible thing. And that's an important point, but we'll get to that a little bit later too. Because notice you're going to get work out of the piston as the gas expands, and you're going to put work into the system as the gas is compressed.
So if you're talking about volume, you can just look at it like displacement,
Right.
If displacement 0, then change in volume is 0.
Right. Total change, if we add up all the small changes in volume, we get 0. So where are we going in chapter 7? Well, we're going to get a mathematical statement on the second law. We're going to discover entropy, which is a property, just like volume is a property. But most importantly, we're going to use entropy to help us solve problems.
As long as it's not B, you'll be all right.
We'll use an S for this one, okay? How's that? All right, so we're going to start with an energy balance in order to derive a mathematical statement of the second law. Okay, so the way we're going to do that is we're going to consider a reversible cyclic heat engine and a system that can take in some thermal energy, not a lot, but some thermal energy, and produce some work. Now, this is not a cyclic thing, so we're not breaking Kelvin-Planck statement of the law. right, of the second law. We're not taking in a net amount of heat and only doing a net amount of work without rejecting heat on a cycle, because this doesn't operate on a cycle. If it did, then we'd have to reject some waste heat, or we would get no work done, right? Make sense so far? So don't worry about all these little deltas here. We're just saying these are inexact differentials. And this means the same thing that a D means, essentially, except that it's not an exact differential, it's just a small amount also. So we put in a small amount of heat here from this reservoir at temperature TR. We let some of that thermal energy be changed into a small amount of reversible work. And then we reject some waste heat to another system, allowing that system to also do some small amount of reversible work. Okay. So this is a combined system. It consists of two different work-producing devices, one operating on a cycle, one not. We're going to take our system down here around the whole thing. So writing an energy balance for this, the amount of combined work, these two together, the small amount of work we get out of the non-cyclic engine and the small amount of work we get out of the cyclic engine will be the combined work, and they go right here. Now, what will happen though is we will have deposited some energy here, some thermal energy, and the system will have changed its energy a little bit. Now this doesn't look like a balance in the way you normally see it, because we have a withdrawal here, a deposit here, and a change of account balance here. Probably a better way to write that would be like this. Let's see, the deposit, DQR, less the withdrawal, the combined work, equals the differential change in the energy of the combined system. Now, why do we have these odd deltas here and a D here? It's because energy is a property of the system. It doesn't matter how you add and subtract energy. If you get it back to the original state, it will have the exact same amount of energy that it left with. So the change in energy would be zero. Okay, so this is one of those exact differentials things.
Those are both deltas here.
Yes, these are both deltas despite my poor handwriting. Yep.
Okay.
Okay, and all they mean is a small amount, just like that means a small amount.
Okay.
But once again, these are inexact things, and this is an exact thing. You don't have to worry about exact versus inexact too much. We're just working on deriving something. Just stay with me, and once we get to the end, I'll show you what's important. Okay, so this is just that equation rearranged a little bit. Okay, deposits, withdrawals, is account balance, that all. That's all. Okay. Now we know that for a reversible heat engine like this one, we know that the ratio of the heat flows is equal to the ratio of the temperatures across the heat engine. So we have some intermediate temperature T here, lower than TR. It doesn't matter what it is, we just know it would be there. And that temperature ratio of TR over T would be equal to DQR over DQ. Gary, sounds like we're about to go have food, right? Now we're hungry.
Don't tempt me.
Okay. So we can rearrange this equation and solve for the small heat flow from the thermal energy reservoir. We're just rearranging this equation and moving the DQ to the other side. And then we will plug that into the energy balance to get rid of the DQR. Okay. So once you do that, here's the energy balance. Now don't panic about this equation too much. Don't worry about the differentials. There's no calculus here that you will have to perform. This just means small amounts of things. Okay, that's all this deltas and D's mean.
Does that equation change when it's not a small amount?
We will eventually have to integrate it, but we'll do that in a minute. Because the integral of that equation will be very interesting. So from the last slide, we had this system, and we have this energy balance, essentially. That's what we have. Okay. Now, if we wanted to integrate this on a cycle, in other words, if we want this system to come back to where it started, we want it to give us some work and come back to where it started, then we would have to integrate both sides of these equations. And on this side, we'd have to integrate over a cycle. Okay? And so the amount of combined work we would get would be TR, because TR would come out of the integral because it's constant. And we'd have this dQ over dt. But if we integrate over a cycle, since energy is a property of the system, the integral over cycle of volume, remember, was zero. Well, since energy is a property of the system, any small change of energy integrated over cycle would be zero. In other words, if you deposit and withdraw money from the bank account, and your deposit's equal to your withdrawal, so that your bank account is back where it started, the change in account balance is zero. Okay, make sense? Because your account balance is a property of your account. Same thing here, energy is a property of this system. Okay? So if we actually operate it on a cycle, then we'd have to, I mean, basically this term would go away because it would be integrated over the cycle. So this is the amount of combined work we would get out. Now, could we operate this on a cycle and get work out of it? No. Right? There's no way to operate this system on a cycle without rejecting some waste heat and getting any work out. So what that tells you is that the combined work of these two must be less than or equal to zero. There's no way that we can do this. We have to reject heat. Notice that ultimately, if we don't get to actually reject heat from this engine, then this engine can't do any work either. So these two together would have to give us an amount of work that is less than or equal to zero. In other words, what we could do is operate this in reverse and let thermal energy flow from low temperature to high temperature, or no, I'm sorry, from high temperature to low temperature. That would happen automatically, but we wouldn't get any work out of it. Okay?
So energy is a property of the system, is that because the thermal reservoir is an infinite thermal reservoir?
Yeah, the amount of energy that we have in the system is just a property of the system itself. Because we're not in, our system boundary does not include the thermal energy reservoir.
Oh, okay.
So we know that the amount of work we can get on this thing is less than zero. In other words, this is a useless device, right, for practical purposes. But for deriving an equation that tells us something interesting, this is a useful result. So since the absolute temperature TR is not the part that's less than zero, it must be this integral that's less than zero. And that was the Clausius statement of the second law. That's the mathematical Clausius statement of the second law. Okay, fine, whatever. If we allow this system to become an internally reversible system, then let me think for just a minute.
Can I interrupt your train
Yeah,
of thought?
please.
So the temperature, your TR, is
Yeah.
that your temperature? Your TR is outside the system
Right,
in this case, though.
correct.
So in my brain, I'm
How did it
thinking-
end up in the equation?
Right.
Okay, it ended up in the equation.
Because I think, I only understand this to be for the energy to be zero, it only makes sense if your reservoir is outside of it. Because then you can only meet a certain efficiency between your two temperature differences. So let's say it's.
Well, don't get too confused there. All we're saying is that the thermal energy reservoir has a temperature TR at which it can transfer thermal energy to the system.
Okay.
And then, I think the part you're missing is that if we operate the system on the cycle, then we can't actually transfer any energy to the system and get any work out.
Okay.
I think it's this cyclic part that you're missing.
Okay.
Anyway, for an internally reversible system, if we were to operate this on a cycle, we should get more than or equal to zero. So if the entire system, so that means the combined work would be more than or equal to zero. But we've already shown that the combined work must be less than or equal to zero. So the only possibility is that the combined work here would be exactly zero if both of these are reversible. Okay? So what that means then is that for an internally reversible system, this integral is equal to zero. Now, why would we be clear about that? Why would it make any difference? Because it's a brand new property. Okay? Like I said at the beginning of this discussion, if you have a property of the system and you change that property and add up all the small changes as you go along, but then return it back to where it started, then you will get zero. You do the same thing with energy, you'll get zero. Okay, so we're talking about internal energy. If you integrate internal energy over a cycle, you'll get zero because the system will come back to where it started. It won't have any more or less energy. How do you know? Well, because if you're going to come back to the exact same state, all the properties of the system must be exactly as they were when you started. Otherwise, you're not at the same state. And that's the definition of a cycle. So if we have any property and we integrate it over a cycle, if we allow the system to go through a cycle and integrate it and get a zero, we know we have integrated a property. Therefore, this little thing, dq over t, that is a property. That's the important result here, is that ds, the differential change in entropy, is defined as a differential heat transfer divided by the temperature at which the heat transfer takes place. It has units of kilojoules per Kelvin. Go to the back of your book, and you'll see that entropy is listed as a property. You can look it up. If you look up R134A, or you look up water, or even ammonia, you find entropy as a property. Now, they give it to you instead of in kilojoules per Kelvin, they give it to you in kilojoules per kilogram per Kelvin, because they want to make it a specific property, a per unit mass property. Okay? The point here is that we've got a new property, and if we can tabulate that property, we may be able to use it to solve some more problems that we could not before. Okay? All right. So if entropy is a property, now be careful, because there is this internally reversible caveat here. Okay? We understand entropy for an internally reversible system, but not for something that's not internally reversible, at least not yet. Because that seems pretty useless, because there's no such thing as a reversible or even an internally reversible system. But it'll help us with real systems in just a minute. So if we had some system that was moving along a reversible process path, and we could talk about the entropy of the system at two states, then we could talk about the change in entropy of the system between those two states. Okay, fine. Just like if we had volume at one state and volume at another, we could talk about changing volume between those two states. Okay. All right, so if we were to take this equation and integrate it from state 1 to state 2, then the change in entropy between state 1 and state 2 would just be the integral from state 1 to state 2 of dx, this property. Now, why are we talking about this? Because this doesn't exist anyway. I mean, internally reversible systems don't exist, so why bother? It's like a mirage in the desert, right? Well, why would we care? You guys ever seen The Shakiest Gun in the West, Don Knotts? Okay, well, it's an older movie, but I love Don Knotts. I think he was great. I really like him to Ken Conway. Anyway, he, of course, it's a Western movie, so he has to end up in the desert lost, right? So he's walking along, he's leading the horse eventually, because the horse can't carry him anymore. And he's saying, water, water, I need water. And of course, there's a mirage right in front of him. He thinks it's water. He falls into it. He starts slurping it up in the sand. You know, this happens a couple of times, right? Because this is a 60s movie. Finally, he comes to some water, and he looks at it, you know, and it makes the same noise again. He goes, it's not water. He keeps walking, of course, falls into the water, right? So anyway, this is a mirage. Why would we be concerned with this? We're interested in it because finally we'll be able to talk about the entropy change for a real process. And that is something that will be very, very useful. Okay, so we know, going back to our original equation, that any real system is going to have an integral here that is less than or equal to 0. Okay? Equal to 0 if it's reversible, less than 0 if it's not reversible, which every real process is not reversible. So let's consider a cycle. If we're going to integrate on a cycle, let's consider a cycle that consists of a reversible or irreversible, in other words, this could be our real path, and a process that consists of an internally reversible path. Okay, so that we can talk about the entropy change for this path and relate it to the entropy change of the real path. Okay? So we could break this up into two parts. We could break it up into an integral from state 1 to state 2 here, and an integral from state 2 back to state 1. Okay? So this cyclic integral has been broken up into two parts so that we can actually move along a cycle. Okay? So all I've done is change this into two pieces, and it still has to be less than or equal to 0. Notice one of the process paths is a real process. The other one is the reversible one, at least internally reversible. Okay? So what this tells us, from the last slide, let me back up. When we looked at the change in entropy for an internally reversible process, we saw there was just the difference in entropy between the two states. So you could look up the entropy of water, for example, in two states and take the difference, okay? But that would just give you the difference in entropy when an internally reversible process on that water had taken place, okay? But real processes of real water are not internally reversible. But here's the point. The internally reversible integral is just delta S. So let's plug that in. Notice we've got it right here. So this internally reversible piece we're just going to replace by it'll be S1 less S2. Okay, and then when we pull it to the other side, then we'll have S2 less S1. And, well, actually, I'm sorry, I'm confusing myself. All I'm doing is from the previous slide showing what this bit is right here. Okay, from the last slide, we had S2 less S1 for an internally reversible system is this integral. So now finally we can plug it in here. Okay? So we still have this integral to deal with here, but we have S1 less S2 from this integral. Okay? Now, I don't know about you guys, but I don't like less than or greater than signs. I like equalities, because that's the kind of equation that I know how to solve. So at this point, rearranging just a little bit, we have an inequality. We have the integral of the entropy for a real process has to be less than or equal to the entropy change between state 2 and 1 for the reversible process. So what this tells us, if we want to have an equal sign in here, is we better add something, let's see, to this side to make it bigger. Does that make sense? So we need to add something to this side to make it bigger so that we can have the equality. Then S2 less S1 is equal to the entropy change for a real system plus some generated entropy. What the heck does all this mean? What this means, yeah, it does sound like,
Well,
it's more marketing, right?
You're actually calculating the area under the curve between 1 and 2 of the two different paths. So the
Got it.
difference is the area in between the two.
You're absolutely right. In fact, that area represents the amount of generated entropy. That's right. Okay, so because you're on this axis, you're going to have entropy as the property. But anyway, the point here is that entropy is generated by real processes. And so any real process is going to generate some entropy. And what is entropy? Well, entropy can be thought of as randomness. It can be thought of several different ways, but randomness is probably one of the best ways. But the point is that even an isolated system, a system that is not doing anything with the rest of the universe, will generate entropy. Remember when we watched the Vsauce video last time? He was talking about, didn't see it?
No, I was here.
You were here, you were present in body but not in mind, right?
Yeah, man, chapter 6.
Chapter 6. Well, he talked about the heat death of the universe, where eventually everything would be spread out evenly, right? I just thought of a joke, but I'm not going to tell it. It's a bad one. Not a dirty one, just not very good. Anyway, what he's talking about is the fact that everything we do generates entropy. As the sun continues to burn, if you will, and it's a nuclear furnace, it generates entropy. Everything that moves forward, every process that occurs, generates entropy. Okay? And that's why he was saying if you lay on your couch and do nothing, you generate less entropy than if you, for example, go and start up your car and drive it down the road. Okay? So anyway, real processes generate entropy, and any process that moves forward will also generate entropy. Remember, we started out our discussion in chapter 6 talking about different processes that would or would not occur according to the first or the second law. And both the first and the second law had to be satisfied for a process to actually occur. All right. Well, the first law, of course, is energy conservation, but the second law is that entropy has to be generated before a process will occur. Okay? Entropy is something that we get for free that we don't want. It's generated, it's not destroyed, it's just generated from nothing. Okay? So for a real process, which is an irreversible process, the amount of generated entropy would be greater than 0. For a reversible process, the amount of generated entropy would be equal to 0, and it's impossible to have entropy be destroyed. So that's why Vsauce, what is his name?
Michael.
Michael. That's why Michael was talking about the mark that you make on the universe that no one can erase, is the entropy that you generate. Now, it's not necessarily that we can go back and look and see entropy and see what people have done in the past. It doesn't work that way. But you do leave a permanent mark on the universe just by living.
That would make history a lot easier.
It would, wouldn't it? If you could just go back and see what people have done. It would also make court cases a lot easier too, wouldn't it? No way. So the point of all of this is that processes only occur in one direction. What direction? The direction that will generate entropy. Okay, entropy is not conserved. It's created from nothing. Here's the important part that you care about. The performance of engineering systems. What kind of engineering systems? Pumps, motors, air conditioners, compressors, anything that does something. The performance of all engineering systems are degraded by entropy generation. The more entropy generation, the worse they are. Okay? And generated entropy is a measure of how poorly the system will perform. What is entropy though? How else can we look at it and understand it? Well, entropy can be looked at in terms of thermodynamic probability. What the heck is that? Well, let me make a graph for you that might help explain it. Consider a particle. Let's say that there's a particle and you're on the really small scale, right? Extremely small scale. You guys have probably heard that time and space are quantized, right? You've heard that before. You may not know exactly what it means. I don't know that I or anyone else knows exactly what it means. But the point is that stuff doesn't exist at just any point in space. It exists in discrete points. And if you could zoom in far enough, you could see that the atom, let's say it's an atom of whatever, exists here. It doesn't exist in between, and it re-exists over here as it moves, okay? The distance between these points is really, really small, okay? But just for a minute, imagine with me that we've got this 4x4 grid, and this is some type of container holding the molecule in place. It has no dimension this way, so the molecule has to exist in one of these 16 different locations, okay? How much entropy would this molecule have in this container? Well, we need to know the number of possible arrangements of the microscopic system. There's 16. So we'd have to take the natural logarithm of 16, and k is I've forgotten what constant it is. It's named after someone, but it's a constant, so that you can look up. And you can calculate entropy. Now, what if we make this a larger container? Essentially what happens is the potential for randomness increases. Okay? Because this particle, if it has any thermal energy, it's going to be bouncing around. So now there's 25 different possible places it can go. Right? So the thermodynamic probability of it being in one particular position is pretty low. So it turns out that since there's more probable locations, the entropy is higher. Another way of looking at this that may make more sense. Let me find the video. There's an entropy video, and the sound on it is really loud, so hopefully I can make this work. I always have trouble with the video run. Let's see if we can make it work. Except I think that Windows Media Player will not play QuickTime files. Yeah, it's amplified. Yeah, it'll play the sound, but won't play the video. Let me try again. Hang on just a second. Let's see if Chrome is smart enough to play QuickTime.
See, why can't it just have a definition? When the definition of something is a somewhat abstract property, I mean that,
It'll get better, just wait.
I'm looking at it with a sense of humor, though. It's not, you know, it's like the second time through, you don't know that you're okay.
That's right. It's weird, but you're used to it, so it doesn't matter. Let's see. You know what? I think the VLC will play it. That's how to use it. Hang on. All right, let's just download it quickly. It won't take too long. Don't keep me up to date, just download it. Only 40 megabytes. should find a version of it that is on YouTube.
You showed us one last, that thermal one, last time.
Probably showed you this one.
You showed us one about, marbles in a box. And that's how you kind of explain entropy. You said it can't get undone.
Right, I can show you that video again too, if you'd like to see it. I'm not sure that everyone in here has seen that video, so it's worth watching already.
As long as you ask the question again, because now I know the trick, so.
Yeah, this one, marbles defy entropy. Is that the one you saw?
Yeah.
Now check this out. What do you guys think of this? So you see the marbles, right? And you hold the container, start shaking it around. Doesn't seem too interesting for a while. Something kind of strange seems to be happening. You see what it is? Yeah, the blues are coming together and the reds are coming together. Some kind of trick. What is this? Would that ever happen in the real world? Depends on what.
Mathematics and lots of shaking.
You could, like, you have to do something.
You could set some type of, yeah, do some external.
You cannot make that
You have
happen.
to do something that's external to the system. You can't just randomly
Yeah.
shake them around. Because that's one potential configuration, right? But there are a lot of other potential configurations where they're mixed. And there's so many more of those, that's where it's going to end up, right? And so, do these marbles actually defy entropy? Because the idea of entropy is that randomness increases, right? Entropy is generated. Okay, so if you take a bag of marbles or a box of marbles like that, you shake it around, you're going to increase the randomness because the process is moving forward. Okay? So what do you think happened in that video?
It's got heavy marbles in there.
He's got heavy marbles and light marbles and something else up there.
He filmed it and then, put it on backwards.
He filmed it and put it on back. That's exactly what he did. Because that would never happen. That's not fair. Can't do that.
Everything starts out nice and easy when they wake up, by the end of the day,
Okay, let's see if QuickTime will automatically play. Oh, wait a second. Let's just do this. Okay. So this is an experiment. What's going on here is you've got two different glass cylinders, essentially, that can hold molecules. So you're going to see all these green marbles over here represent molecules, maybe air molecules, maybe hydrogen, helium, whatever you want it to be. Because they have thermal energy, they're going to be bouncing around. Now there's a stopcock in between the two to prevent the gas molecules from going to the other side. But essentially the pressure on this side would be a vacuum because there are no molecules in it bouncing around. So as the molecules bounce around, if the stopcock is open, eventually some of the molecules will make their way to the other side. And the pressure essentially on the two sides would equalize. Now, what has happened? Just a second. What happened when we opened this up and some molecules went over here? Was that a reversible or irreversible process? Irreversible, right? Because it would not naturally do this. That would never happen. Where all the molecules just happen to move to the other side, and we can close the stopcock. Why would that not happen? Because as soon as you open the stopcock, the number of potential configurations explodes. In other words, the number of positions these molecules can occupy becomes much, much larger. And basically what's happening is by virtue of doing that, by exposing those molecules to more space, you've increased the entropy of the system. Does that make sense?
So you increase the entropy which is being generated.
You've increased and generated. You've increased by generating.
All right.
And you know that it's irreversible because you know entropy has been generated. that's the end of that particular slide, or not slide, but video. Another way of looking at this. If you had a pure crystal that was at 0 Kelvin, you would know the location of every single molecule in that crystal exactly, right? There would be no randomness, there would be no variation in position. And so you would know the location of everything. Now the temperature would have to be 0 Kelvin, because if there was any thermal energy, those molecules would be vibrating a little bit and you wouldn't know their exact position. There would be some entropy. Okay? So the idea here is that a pure crystal at 0 Kelvin has an entropy of 0. Why? Because the number of different arrangements of those atoms is 1. There's only one position they could all be in. So the thermodynamic probability is 100% that it's going to be in one particular configuration. The natural logarithm of 1 is 0, and so the entropy is.
So what you're saying is that 0 Kelvin is impossible for multiple reasons?
I think so, but I'm not sure that I understand it enough to say that. Here's another example. Mom, it isn't fair for you to spend the morning folding our laundry. Would that ever happen? That's one possible configuration,
I don't
right?
like, I don't like your odds.
I don't like the odds either. I wouldn't bet on it. So finally, since entropy is a property, we can use it. Okay, now we get into the interesting part. How do we use it? Well, we can make a TS diagram if we want to. We can use entropy as any axis and use it because now it's a property of whatever fluid we're dealing with or whatever system we're dealing with. So we can have a vapor dome on a TS diagram. We can do various experiments and plot the entropy versus temperature or pressure. And see the same type of results that we saw before. On a TS diagram, though, the pressure line here is almost on top of the saturated liquid line, not quite, but almost. Some other features of a TS diagram is that in the saturation region, lines of constant pressure are parallel to a line of constant temperature, which is not really a surprise because if entropy is the property of the system, and we've already defined one property, right? Because we've defined the temperature and we've got a mixture of liquid and vapor here, all the other properties have to be set, such as volume and entropy. Now you might look at this and say, well, wait a second, the entropy is actually changing, the entropy is decreasing, and I can see that the volume is decreasing too, the specific volume will change. Well, that's because there is liquid and vapor present together. And so the entropy of all of the vapor is right there. It actually does not change. The way that the entropy of the system changes is because some of the vapor goes into the liquid phase and picks up entropy right there. Does that make sense? Yes, no, comment? Just like volume, if you were to look at the specific volume of a saturated mixture, the average specific volume would be the total volume of the system divided by the total mass. But the specific volume of any vapor would be the specific volume of saturated vapor, and the specific volume of the liquid would be the specific volume of saturated liquid. Okay.
So you can find the specific entropy of a system using that same formula we've been using.
Exactly. What you're saying is that formula we had before, Y,
I don't think it's called that formula, but that's what I call it.
that's fine. It's the lever arm rule. Okay, Y average equals YF plus X YFG. You can plug in entropy for Y. It works just fine.
It looks like 1 over F.
1 over F. Oh, yeah, it does.
YF.
Here, I'll fix it. There we
Put up some slack
go. Okay? No, you're fine. In the superheated region, what you'll notice on a TS diagram is that lines of constant specific volume are actually steeper than lines of constant pressure. So there's some various features of a TS diagram. Now the TS diagram is really interesting because if we were looking at an internally reversible process that moves from one state to the next, the area beneath that curve represents something important. Because remember, the definition of entropy was that S is defined as a differential amount of heat transfer divided by the temperature at which that heat transfer takes place. So we could rearrange this equation and solve for the differential amount of heat transfer as, I'm sorry, I didn't mean ds, I forgot that, as T times ds. Okay, so for a differential change in entropy multiplied by the temperature at which the heat transfer takes place, changing the entropy, this area is equal to the differential amount of heat transfer either to or from the system. Okay? So if we are interested in what goes on from state 1 to state 2, we can add up all this area, and for an internally reversible process, it will be equal to the amount of heat transfer that occurs. And I meant to have that equation come up on the board. I'm sorry. Those two should have come up before I. Now, why would we care about this? Well, remember PV diagrams? When you first saw a PV diagram, you probably weren't too enthralled with it or too velocity or too interested in it, but then you found out that the area beneath the curve represented boundary work. Remember that? We had several different boundary work equations, and we found out that we could use them and they were useful in solving problems. Well, this will be useful in solving problems as well. In fact, there are some processes that are special processes. There are processes like this one that is in a so-called isentropic process. What happens here is the system moves from one state to the next without changing any entropy. Okay, so all that happens is the temperature decreases. Is that possible? Yes, it's possible. But if it's a process that actually goes forward, you know entropy is going to be generated somewhere else and added somewhere else. But in this particular system, the amount of entropy of the system does not change. Now what's interesting about this is that if on a TS diagram, the area beneath the curve represents heat transfer, then with a vertical line, there's no area beneath that line, right? So there must be no heat transfer, which means that this is an adiabatic process. Since the entropy of the system is constant, then this is at least an internally reversible process.
So basically the volume just changed.
No, the volume doesn't necessarily change. We don't have volume on either of these axes.
So
All we
that's
have
what I was
is
trying to figure out
entropy.
how you would have your temperature decrease without affecting your entropy.
Okay. I understand.
So-
And we'll get to that in just a minute
Okay.
because entropy has more to do with heat transfer than it has to do with temperature.
Okay.
You could change the pressure also and keep the entropy constant. Okay. Or you could change the volume and keep the entropy constant. Okay. But anyway, I want you guys to write something. Remember how I had you write delta H equals Cp delta T and delta U equals Cv delta T? Probably good practice to go ahead and write that one for me. I was trying to drill into your heads that Cv is associated with delta U, Cp is associated with delta H. Well, I want to give you something else to write. It is something I want to drill into your brains as well. And that is that adiabatic, now this is not a real equation, it's just a memory trick. Adiabatic plus reversible equals isentropic. So if you don't take notes, please at least write this down because I'm just trying to drill it into your brain and make you remember that. If you have a process that is adiabatic and is reversible, it will be an isentropic process. On the other hand, if you have an isentropic process, it will be adiabatic and reversible. Okay?
Reversible means that it can be.
It can go forward and it can go back to exactly where it started without affecting anything else. Now, so far, this is still kind of theoretical and not all that useful. Okay? But we'll get to a point that's really useful here in a minute. Now, in the case where you have a constant temperature process, then the area beneath the curve represents the amount of heat transfer that takes place. So you can calculate the amount of heat transfer if this is an internally reversible process as the temperature multiplied by the entropy change. Notice that would just be the area of a rectangle. Delta S would be the base width of the rectangle. The temperature would just be the height. And you have to be careful here because notice that this temperature would have to be in absolute units, otherwise it wouldn't work. So when you're dealing with entropy, a lot of times you have to be careful and put your temperatures in Kelvin, but we'll get to that later. We can also calculate the specific heat transfer as the specific entropy change, but we'll worry about that later. Okay, so for this case, the amount of heat transfer is 0, and I should have had this one come up before that one. So anyway, this is 0 because there's no area beneath the curve. Can entropy be transferred? Well, actually, yes, it can. Entropy can be transferred between systems. It turns out that, let's say you have a system where you're maintaining the system boundary at 400 Kelvin, and you want to transfer 500 kilojoules of thermal energy in, okay? Or 500 kilojoules of heat in. If you force the temperature to remain constant by allowing the piston to move up and down, or moving the piston up and down, such that the temperature remains at 400, then the amount of entropy that you transfer to the system would just be Q divided by T. Because this is a process that's going to occur. We're going to let heat transfer in, we're going to make the temperature of the boundary remain constant, the temperature of the system remain constant. So this is heat transfer at constant temperature, and according to the last slide, assuming we don't have any friction with that piston, what will happen is there will be a change in entropy of the system, but the temperature will remain constant. Okay? So the amount of entropy that we carry into the system would be equal to the ratio of the heat transfer to the temperature. So we take 500 kilojoules, divide it by 400 Kelvin, and find out that we've transferred 1.25 kilojoules per Kelvin of entropy into the system. Here's what you need to remember. Heat carries entropy with it. Anytime you transfer heat into a system, it will increase the entropy of the system because it's carrying entropy in. Anytime you take heat out of a system, you will carry entropy out of the system because heat always carries entropy with it. So that may be one thing you want to write down along with this, is that heat carries entropy with it.
And that's true on, did you say constant temperature?
That's true anytime, even though we talked about it for constant temperature.
Heat carries entropy.
Heat carries entropy with it. That's right. That's one of the reasons that heat is a less valuable form of energy than is work. Because work doesn't carry any entropy with it, heat does.
Can that be our quiz?
Could that be a quiz? I would hesitate to give you a concept quiz over this stuff.
I think you may have meant that question specifically. I wouldn't battle that, so I'd be fine.
Now, it turns out that mass can carry entropy with it as well. If you have some kind of control volume and you have mass coming in, not only will that mass carry enthalpy, it will carry entropy in. But mass can carry entropy out as well. Now, let's imagine for a minute that we have a system that is insulated. The piston is frictionless, so it's reversible. Okay? And we have air inside of this system, and we have a paddle wheel. So we turn the paddle wheel, okay, and the blades cause the air in here to move around. Maybe the temperature goes up a little bit, but then the system does some boundary work, so we have some boundary work flowing out here. Is that a reversible process? Could we expect to compress the gas, have the temperature go up, cause the propeller to turn and get work out? Of course not. It wouldn't work in reverse. So we know entropy must have been generated here. All right? We know the entropy, though, is not transferred by work. How do you know that? Because I told you I haven't proven it, but take my word for it. Where is the entropy? How come the entropy of the system is increased? How come entropy has been generated here? It's because of friction of the blades. As those blades slice through the air, there's viscosity in the air, and that's how the temperature of the air goes up. But that's an irreversible process. This is the place where the entropy is being generated. It's not actually being carried into the system via the work. Okay? So this is a case where entropy is being generated, not transferred. Okay, so that's Jim goes with that particular example. Now the Carnot cycle on a TS diagram looks a whole lot more normal. Remember when we saw it on a PV diagram and it had 4 different curved slope things? Looks strange. Well, on a TS diagram, it actually is a very regular shape. It's a rectangle. Let me show you how it works. The first process from state 1 to state 2 was a thermal energy addition process at constant temperature. So it was a reversible heat addition process. Right? How are we doing on time? It's about time for a break. Let me get through this slide and we'll take a break. Okay? So as a constant temperature, heat addition. When you add heat, what else do you transfer in? Entropy. So the entropy increases. In fact, this area represents the exact amount of heat transfer from state 1 to state 2. It's kind of interesting.
So you're saying when you add heat, but the temperature stays the same,
Yes. Now, how could you do that? How can you add heat and have temperature stay the same?
the volume
The
changes?
volume
Volume
changes.
changes, the volume increases. The pressure might change too, but the volume increases and allows the temperature to remain constant. Okay. So reversible isothermal expansion is the first step in this process. The second step, or the second process in the cycle, is reversible adiabatic expansion. So here we've insulated the top of the cylinder. We've allowed the piston to move down, doing more boundary work such that the temperature drops from TH to TL. Now this is a reversible, no heat transfer process. So it must be isentropic. In other words, the entropy is constant, it's a straight vertical line. There's no heat transfer during that process. Not surprisingly, there's no area beneath this process curve. And the entropy remains constant. So that's the process from state 2 to state 3. From state 3 to state 4, we had reversible isothermal compression. So we put our energy sink here, we compress the gases at constant temperature TL, transferring heat out. So once again, that's going to be a process. It's sort of like the opposite of this process. Okay? From 3 to 4, the temperature remains constant. We transfer heat out. That heat carries what with it? Entropy. So the entropy goes down. And this area represents QL. Okay? From state 4 to state 1, we put our insulation back on the top of the cylinder, continue to press the gases such that we move from TL to TH and come back to state 1. Well, there's no heat transfer. This is a reversible process, so it's isentropic. And if we stop at state 4 just right, we'll move right back up to state 1. Okay? Now, the amount of area enclosed by this box, notice, is equal to the net heat transfer. Because remember, this area is QH. This area is QL. The difference between those two is this area, which is the net heat transfer, which is also equal to the net work output of the system.
Can we ring up the lab?
Yes, please. No, it's the last one. No.
He's
Somebody's house
swirling.
there, isn't it?
He just
Okay, so the net work output is QH minus QL. So, okay, this is all fun and interesting, or at least we can pretend that it's interesting, right? Awesome. So what are we gonna do with this stuff? Is there any real use of this property? Well, remember, when we had a throttling valve and we used an energy balance to find that the enthalpy in equals the enthalpy out, that was actually useful in solving problems. Remember? Well, it turns out that a lot of devices operate pretty close to isentropically. They operate without changing the entropy of the flowing stream. So nozzles, diffusers, compressors, turbines, and pumps ideally all operate isentropically. In other words, the entropy of the incoming stream should be pretty darn close to the entropy of the exiting stream. There's not a lot of irreversibilities in most of these things. Now, anytime you have heat transfer, that's an irreversibility. So this particular compressor wouldn't be modeled well with entropy because entropy is being generated due to this heat transfer. It's also being lost from the system due to the heat transfer. So the entropy would not be constant across that compressor.
So a lot of these homes are probably gonna have to work adiabatic.
That's right. A lot of these problems are going to be adiabatic and reversible, so they're going to be isentropic problems. Okay, but let's see what kind of equations we can use to start with. So ideally, these devices work best when there is no friction or any other irreversibilities. Now that makes sense, right? I mean, a pump with a lot of friction is not a good pump, right? It's something that needs to be fixed or replaced. Okay? A steam turbine that has a lot of friction in it and a lot of unrestrained expansion of gases where the gases can just flow around the blades without causing the blades to turn, it's not a very useful system, right? That's, both of those are examples of irreversibility. So ideally, these devices would have no irreversibilities and so would generate no entropy. The heat transfer is approximately 0. No entropy is transferred into or out of the system, therefore, and the entropy of the incoming and leaving streams would be about equal to each other. That's another constraint, that's another piece of information that we can use.